Over and over again, my physics students will say to me, I just don't get the photoelectric effect. And why is this? Well, I think there are several foundational pieces of information that you have to have clearly in place if you've got a hope in heck of understanding this topic. Please let me know in the comments below if you think this attempt of mine to simplify things has helped you. The first of my basic points that you have to understand is all about the electromagnetic spectrum. You need to be fully aware that the electromagnetic spectrum is considered to be made up of tiny, discrete little packets of energy called photons. The order of the spectrum is dependent on the frequency of these photons. And we know that the energy of these photons is given by E equals hf, where h is Planck's constant. If you are ever unfortunate enough to be hit on the head by a tennis ball, you will know that you feel a short, sharp shock. Clearly, the tennis ball comes zooming in, hits your head, gives you some of its kinetic energy and bounces off with the remaining energy. Photon interactions are completely not like this at all. They are what we call a one-to-one affair. A photon comes flying in, it hits the particle, gives up all of its energy and ceases to exist. Now that we've seen that the photon interaction is one-to-one, all or nothing, let's consider what happens if you turn up the intensity of a light source. Firstly, consider a sound wave being produced by a loudspeaker. You know the cone goes in and out, produces rare fractions of air. We draw this as a sine wave for convenience. So, as we turn up the volume of the sound, the amplitude of the waves increases. More energy, louder sound. But you can't take this logic and apply it to a photon, because if you turn up the energy of a photon, its frequency will change. And so, if you want to make your light brighter, you would imagine that the colour would change, but it doesn't. What happens if you turn up the intensity of a light source is that you create more discrete little packets or photons with the same energy that you had originally. So in other words, turning up a light source, making it brighter, does not increase the amplitude of the photons. No, it doesn't. What it does do is just increase the number of them. Point number two in my fantastic list of things to understand about the photoelectric effect is the structure of metals. We know that in a metal like copper, we have a whole pile of copper atoms in a nice neat lattice, though really we should call them copper ions, because each of these atoms or ions donates one or maybe two or a small number of electrons to the sea of delocalized electrons around it. Now, this word delocalized means not local. In other words, free to travel away from the local area. And so these electrons, they zip around all through the structure, having collisions here and there with some of the other atoms, or indeed ions, and even with each other probably. But do remember that my diagram is absolutely nothing like it really is. It's completely not to scale. We're talking models here, like we do all the time. And this leads me to another important point that's often confused here. Naturally enough, these copper ions have a whole pile of bound electrons that orbit, in speech marks, the copper ions. And these bound electrons play virtually no, if indeed no, role at all within the photoelectric effect. Point number three in my essential list to understand is to consider how waves deliver energy. Energy is delivered continuously by waves. Now, you know this is true. If you get a chess ball and put it outside in the sunshine, if we ever get any, then you will know that the black squares on that chessboard are going to warm up gradually. In fact, they can get quite hot. And this is because they are absorbing the infrared waves that keep falling on them continuously, over and over. Pluck a guitar string and you'll see the string vibrate like this. And as it's vibrating, you hear this continuous tone. Consider too that loud sounds, waves, can cause things like wine glasses to build up such a big vibration that they just shatter. And now we have arrived at the place where we can begin to talk at last about the photoelectric effect itself. It's quite a simple practical in some ways. The light source is set at a relatively low frequency, i.e. low energy, and is shone onto the clean metal surface. Nothing happens, and so the frequency is increased. Nothing continues to happen, and the frequency is increased again, and still nothing happens. Eventually though, as the frequency is increased, there is a point where suddenly electrons are emitted from the surface of the metal. If you decrease the frequency a tiny bit to the other side of that threshold frequency, again no electrons. If you keep on increasing the frequency up past the threshold frequency again, you will see that electrons are emitted. And you'll notice that at a particular frequency there is a range of kinetic energies that these electrons, or photoelectrons as they're called, have. There is a definite maximum kinetic energy. As you increase the frequency of the radiation, so you still get a range of kinetic energies of photons given off, but the maximum value also increases. This in itself was all very puzzling. So somebody wondered what would happen if you turned down to the frequency of the light source just below the threshold frequency and just left the setup for a long time. So they did. They left the setup for a long time, enjoyed a very nice pub lunch, came back and discovered that exactly nothing had continued to happen. So somebody else thought, what if we turn down the frequency just below the threshold frequency, but double the intensity of our light source, or quadruple even the intensity of our light source? So they did this, and again, nothing happens. Let's draw some conclusions from all of this. Remember, some of the world's greatest physicist rock stars got stuck trying to work out what was going on. There is a minimum frequency and hence energy below which no photoelectrons are emitted. This suggests strongly that the light coming in is behaving as a particle, because if it was a wave, we know that energy builds up with waves, and consequently the photoelectrons would eventually have enough energy to be emitted. But however long you wait, nothing happens. The fact that there is a minimum energy suggests that the delocalized electrons are held in place by some kind of force that they have to overcome in order to escape from the metal. At a given frequency of incident radiation, we know that all of the photons coming in have the same energy. We also know that we get a range of photoelectrons emitted, and this strongly suggests to us that some photoelectrons find it easier to escape from the metal than others. This is explained because some of the photoelectrons, before they're emitted, when they're delocalized, they're right down deep in the structure, and therefore when they receive their packet of energy, they have to bounce around colliding with lots of particles to get up through the layers before they can be emitted. And this explains why they will come off with less kinetic energy than one that is sitting right at the surface. The minimum energy, therefore, for an electron to escape from the metal is for that electron which is right at the surface of the metal when it absorbs its photon. And we call this minimum energy the work function, phi, and it is a property of a metal. So it's always the same, say, for calcium, it's always the same value. If the incoming photon has the same energy as the work function, then only delocalized electrons that are near the surface of the metal will receive enough energy to overcome the work function. Those lower down, of course, will lose energy as they bounce around, like we said. Therefore, an electron that is sitting right at the surface that is given just enough energy as the work function, or just the same value as the work function, will go pop and just literally pop out of the metal and just hang around just above the surface with no kinetic energy. And we can use this fact to work out the work function, but that's a subject for another video. The value of the maximum kinetic energy increases as you increase the frequency of the radiation. Since the work function is fixed for a metal, this really shouldn't surprise us at all. The photon gives the delocalized electron more energy if it's a higher frequency, so more is left over once it's overcome the work function, meaning more kinetic energy. Given that turning up the brightness of a light source increases the number of identical photons incident on the surface, it shouldn't surprise us therefore that as we increase the intensity of a light source, so we get more photoelectrons emitted. This is totally not what would happen if photons were waves, because as we've said many times now, waves deliver their energy continuously. The ramifications of the photoelectric effect are enormous. It opens up a whole new area of physics. One of the ramifications, though, is that Year 12 and 13 students have been confused ever since. More significantly, though, the photoelectric effect suggests that light behaves as if it is a particle in some situations. Notice I said behaves as if. It's not a particle, but it behaves as if it's acting like one. In other words, it has particle-like properties in some situations. You can't explain the photoelectric effect by suggesting that light is behaving like a wave. which is what you'd have to do if you're going to explain the interference effect. And so you can see this is a really interesting piece of physics, because it's showing us that reality, at least down on a very small scale, is nothing like we experience in our everyday lives. And that is the subject for an awful lot of other videos.